Let's begin the talk. All right, so welcome Anita Rojas. She'll speak on a SAGE package for n-gonal equisymmetric stratification of MG.
Well, thank you very much to the organizers for everything, and in particular for the invitation of talking about this work, and to you all for being here. Well, first of all, the word package is a work in progress, especially after seeing Antonio's talk the last session. This is not that well built. It's more or less a script that you can use, and I will show you how to do it. And it's in fact an improvement, an upgrade of a previous program we had. I mean, script running on Sage 2. I will explain first some of the words here in order to be to fix notation and background. Well, this is a joint work with Antonio Ben and Miguel Tello. So first of all, we are going to be dealing with group actions on Riemann surfaces, and I am going to be interested in genus greater or equal than 2. And an action will be a monomorphism from an abstract group G to the automorphism group of holomorphic automorphism of the Riemann surface X. Hence, we have a covering, which is Galois covering, from X to the orbit surface, and the action is called n-gonal if the quotient surface is P1, the sphere, genus 0. Well, n stands for the size of the order of the group. So the classical theory, X is uniformized by the Fuchsian group, torsion-free, which is called the surface Fuchsian group. So X is the quotient of the hyperbolic disk by gamma. And Riemann existence theorem ensures that G acts on X if and only if there is a Fuchsian group delta containing gamma, and gamma was the one uniformizing X, together with the group epimorphism theta from delta to G, such that the kernel of theta is gamma. Oh, I have a timer here and I forgot to put it, of course. There you go. So it is said that G acts on X with signature gamma M1 and MR, where gamma is the genus of the quotients and the MIs are the branch indices of the Galois covering associated to the action. It is also said that this action is represented by the surface kernel epimorphism theta. And we are going to say that this action is captured by the generating vector, which is the images of this epimorphism theta. And we have to recall here that as we are dealing with the orbit surface of genus 0, the canonical presentation of delta is that one. So there we have this, and the epimorphism theta is captured by the images of the generators. Okay, so we abstract that. I mean, it is a classical theory here that generating vectors capture the action. So a generating vector, it is a tuple. We are dealing with gamma equals 0. That is why I put the definition, appropriate to that setting. So it's a tuple of elements of G, such that generate G, and the order of each Cj is Mj, and their product is 1. And Riemann existence theorem says that there is an action of G with that signature if and only if there is such a generating vector. The thing is that we may have equivalent actions, and that is two epimorphisms define two topologically equivalent actions if and only if there exists two automorphisms, one of delta and one of G, such that this diagram commutes. So the idea is to describe or to count actions in a fixed genus up to topological equivalence. So we need to translate that, or one need to translate that to the setting of generating vectors. So in terms of generating vectors, two actions of the same signature are topological equivalent if and only if the corresponding generating vectors lies in the same class under this action over the set of all possible generating vectors. I will describe roughly this action, but the core here is that we have a translation from a geometrical problem, which is classifying group actions under topological equivalence, to an algebraic problem, which is to count generating vectors of a fixed type up to some action. So this theory was used several, I mean, it's very fruitful in the theory of Riemann surfaces and with group actions. And it was there, and so as it is these translations, we decided to put that in a program that will be of help to study these things for higher genus and that kind of questions. So just roughly, the action of this part, which is the automorphism group external and internal of G, is as it should be in a generating vector, and this part is a subgroup of the automorphism of this function group delta. And since we are dealing with quotient genus 0, so delta has this particular presentation I showed you before, then the element that we are going to be considering are braids elements acting as braids. So that gives us a way. So since we have this equivalence, we are going to produce all the generating vectors and compute the orbits and the classes under this action. So what is equisymmetric stratification? Well, it was a concept that goes back to Harvey, Macbeth, and more recently, I mean, in the 19th, Broughton described that the branch locus of MG has an equisymmetric stratification. The branch locus corresponds to the surface with non-trivial automorphism group, and you can stratify it by these kind of sets. So let's say that this set will consist on those Riemann surfaces of genus G with the action, I mean, the full group of automorphism is going to be G, and acting with the action captured by the generating vector theta. And sigma is going to be the signature that, of course, can be read from theta, but we are going to put it in order to have more information. And well, the closure of that stratum consists on the surface such that the automorphism group contains something isomorphic to G with the topological class determined by theta. So these are going to be our stratums, and this could be empty in some cases. So now let's move to the motivation and a review of what was already there. For instance, there was an algorithm to study cyclic group actions due to Bujalance, Costa, et al. And another one who studied group actions under some other constraints on the branching data from Magard, Spectro, and Volclaim from 2003. In a joint work with Antonio Ben and Ruby Rodriguez, we wrote a script on Sage to get the symplectic representation of the action of G. So meaning that the representation on the first homology group. To have this action allows us to find several geometrical information about the action. For instance, the period matrix of X, the decomposition of the Jacobian variety, the analytic representation, and so on. So that was our starting point. As we have already this program, we use that to make some upgrades in the direction that I'm going to tell you in what follows. So the equisymmetric stratification will also study in several works. For instance, in 2014, Bartolini, Costa, and Izquierdo developed some routines in GAP in order to study small genera, 2 and 3, maybe 4. So the thing is that we want to improve this and to generalize to a higher genus, because several questions arise from these stratifications. For instance, how much it depends on the stratum, the decomposition of the Jacobian variety, or the representation on the holomorphic forms, and many questions. So since we have this stratification, we want to understand the geometry involved and how much depends on the stratum we are. So, and the next question is, okay, we have this strata, so how they intersect in the moduli space of Riemann surface of genus G, how they are contained, etc. So this last question, which is the last example I'm going to show you, the last application, leads us to study relations between the strata when we have a restriction of the action. Okay, so if we have the action of a group G, of course, every subgroup acts there, but you have to understand the type, the topological type of this action. Okay. So we need to translate this in terms of generating vectors in order to have, again, an algebraic problem that can be programmed. So the last goal I'm going to show you was to how to restrict the generating vector for G and find which is the one that corresponds for every subgroup. So let me move to the computational part. So, well, the first upgrade we include was to make that action inside the algorithm. So to put that action inside the algorithm. So that would allow us to describe all the action up to topological equivalence. So that will be captured in orbits of generating vectors. Let me show you an example, which is going to be the one that I will show you. So we have the cyclic group of order 8 acting in genus 9, and it acts with that signature that can be proved from Riemann existence theorem. So we asked for all the generating vectors corresponding to that signature. So that says, give us that we have 32 actions, but not all of them are independent. I mean, they are grouped in packages of equivalent, topological equivalent actions. So these 32, well, you can put it there. And we need to compute this action of the braid group and the automorphism group. For instance, the automorphism group of C8 is the Klein group. So these 38, at least there are 8 orbits, see? But we have this braid action, which is a little bit more tricky. But then we have this program. So you ask for representative for these 32 actions, and it says that you have 4. So all these 32 group in such a way that you have just 4 different stratum for this action. Okay, so this is the next question, or the last question I want to show you, is how these strata are, at least try to describe how they are geometrically put inside MG, M9 in this case. So this is the action of the cyclic group of order 8 acting on a Riemann surface of genus 9. Okay, with signature, of course, 0, because if you increase gamma, the problem gets tricky. and that signature. Okay. So we already found that we have 4 stratum. Well, another application we did is that we compute all the actions up to topological equivalence from genus 5 to 10. As I said, by Bartolini, Izquierdo, and Costa, you have the classification of genus 4 and maybe 5. And then Broughton classified before genus 2 and 3. And then we did from 5 to 10. And there are other, of course, classifications, but as far as we know, they are not concerned about the topological equivalence. They classified, for instance, Konder and Brouwer, they classify groups acting on some genuses, but we were concerned about the different actions that each group may have. The second upgrade is the description of the intermediate coverings, because when we have this subgroup, here we have, of course, the total covering, but then we can have these intermediate coverings. And so let's call this pH and this pi up to the h. And the thing is that if you know the signature of the total covering, you would like to know the signature of the intermediate. And this is not always Galois. So here you want to describe, well, the degrees, the index of H, but you want to describe how they ramified over the branch points. So we program that. And for instance, here in this example, I changed the group, and I want to study, S3 with acting on genus 3. So here you have a sigma, which has order 3. And here you have tau, which has order 2. And that gives you a signature of genus 0, the thorax quotient, and then 3, 3, no, mentira, 3, 2, 2, 2, 2, that. So that is the action. We want to study the intermediate quotient. So first, for instance, here, I want to study the action of the alternating group here. So what happens when we take quotient just by generated by sigma? So what is there? So of course, this can be studied in an easy example like this one, but when the group gets more complicated, it's these kind of routines are of help. So okay, so we have the first found generating vectors, and it says that there is just one. And then you identify the cyclic group of order 3 inside S3 in order to put it inside the computer. And then we build this routine, intermediate covers, that gives you, well, it is in Spanish, of course, I should have translated. So it says that the quotient by H is 1, the genus, and you have 2 points marked with a 3. So the signature here gives you that you have something like that. Okay. And then the other covering goes to P1, and it is, of course, of degree 2. And it says that you have, here for the global one, you have the sphere and 1 point where the ramification was 3 and 4 points where the ramification was 2. And it says that this doesn't ramify because you already consumed the ramification in this part, and the other one ramified like that. Okay, so you can read that information from there. And finally, the last upgrade is the thing that I said you before, to study these nesting relations between the strata. So given an H and a G and a generating vector theta for the action of G, we find the generating vector corresponding to H. As I am running out of time, let's say that we, to do it, we dig in a classical theorem from Singerman from 1970, where he wanted to study the signatures of the action restricted to subgroups, and inside its proof, his proof, you can extract ideas in order to construct a generating vector related, corresponding to H. So let me finish describing this action I told you before. So we have genus 9 with the action of CH, and that produced 4 strata, 4 stratum, sorry, 4 stratum. Well, the signature was that one. So the dimension of each stratum is 2. And we want to study how these sheets fit inside M9. Okay, so perhaps they intersect and so on. So for that, we need to ask first for all the groups containing CH, the cyclic group of order H, such that the action restricts as we want. You know, we have 4 generating vectors, and the signature of each one is, as I said, 8, 8, 4, 4, 4. So we look among all the groups acting on genus 9 containing CH, restrict the action, and study. Okay, so let me, for instance, to show you with this group, which acts on genus 9, and I ask for how many actions, and it says that it has 5 actions up to topological equivalence, and of course it has 2 cyclic subgroups isomorphic to CH, non-conjugated, and we need to restrict the action. First of all, we compute the signature, as I showed you before, in order to have to identify which generating vectors had the right signature when you restrict to the CH G has inside, and you have to do that for each G containing CH. So that is the routine. Induce generating vector, you made the computations, and let me skip to the end of this story. So we have these 4 stratum for the action of CH, and we can identify them by the different generating vectors, and you study all the groups acting on genus 9 containing CH, and when you restrict to CH the action, you obtain the right signature, and then you identify which stratum corresponds. So you can capture that in a picture. Of course, this is just a picture. I'm not sure if they intersect like that or they are sort of transversal. But the thing is that the 4 stratum for CH are sort of like this. You have one which contains a one-dimensional stratum with the action of the small group of order 16 and number 5 in the small group database. Well, this one I show you is CH times C2. And inside that stratum, one element, if you specialize the coefficient of this family, you can identify that one element has more automorphism and so on. The other stratum has another family of the same group, but different action, different generating vector. Okay, so that is why the action of this of that group in this family is not topologically equivalent to the action of that family. And then the other 2 stratum intersects in a one-dimensional stratum with the action of another group of order 16, and one element has more automorphism too. So that is what I wanted to tell you. So I have some reference there of the classical results I told you. For instance, they have a gap package but not stratification, the signature and the ramification, and this computes cyclic actions, and that is Singerman work, which is the one where you can read the way of restriction generating vectors, although it's not said in that language, of course, because it's from 1970. So thank you very much.
Thank you. Good. So I understood well, and this command intermediate covers this is what you made. This is part of what you made.
Exactly. These commands were not in Sage, and we programmed that, and also that one. And I have the script in my web page. But after I saw Antonio's talk, I want to put it in a package way, even more beautiful, more appealing. But if someone is interested in playing with this, of course, can download our script, and I can help by email if necessary. This is also ours. That's it. Yes.
And how do you enter the group?
Yes, that comes from Sage. So it depends. So for instance, this is one way when you are dealing with cyclic groups, or you can enter by, I'm not sure if I put an example here, by using, which I use a lot, the small group database. So you enter the small group, the order and the name and the number of the group in the small group database. But there's different ways of how to enter. So I'm not sure. Aquí está.
Well, it doesn't matter. That's okay.
Yeah. No, for instance, here you can enter the symmetric group as their own command. And then you can play with our routines. This is Sage, and this is ours. So this is ours too. Okay.
Are there any questions for Anita? Okay, otherwise, maybe we can stop the recording and we have